Good afternoon, everyone. Thank you for joining us today. Today, I'm delighted to introduce Dr. David Larbalestier, who is a professor of mechanical engineering and director of the Applied Superconductivity Center at the National High Magnetic Field Laboratory at Florida State University. He also holds emeritus status in the Material Science and Engineering department at the University of Wisconsin-Madison, which was his academic home until 2006. Dr. Larbalestier earned his bachelor's degree in physical metallurgy from the Imperial College of the University of London in 1965 and PhD from the same institution in 1970. The fundamental interest of his research group is understanding the transport of supercurrent in superconductors and the critical fields. The work in his group is supported by multi-investigator grants from several branches of the DOE, NSF, Air Force, and other agencies. Dr. Larbalestier is a recipient of numerous prestigious awards, just to name a few. He is a fellow of the Royal Academy of Engineering, the American Association for the Advancement of Science, the Materials Research Society, the Institute of Electrical and Electronic Engineers, the National Academy of Inventors, the National Academy of Engineering, the Institute of Physics in the United Kingdom, the American Physical Society. He is the IEEE Council on the Superconductivity Distinguished Lecturer. He received the Cryogenic Materials Award for the Lifetime Achievements from the International Cryogenic Materials Conference 2007. Without further ado, Dr. Larbalestier, the floor is yours.
All right, thank you very much, Igor, and for a very friendly and introduction. There's one correction I should make. I was director of the Applied Superconductivity Center, both in Madison and here in Tallahassee for 28 years, I think, but I stepped down 3 years ago in favor of just going back full-time to teaching and research. And Lance Cooley is now the director, and he has to wrestle with various administrative things that frees me up a little bit. So I enjoyed doing it. All right, so I very much appreciate the offer. What I would say, though, and I put down this title, Materials Challenges for High Field Cuprate Superconducting Magnets, because I mean, superconductors are fascinating materials by themselves, and certainly if you're a physicist and a very fundamental physicist, you know, they pose real challenges. And there's a sense that even now that there would be another Nobel Prize available for the person that really comes up with the explanation of the pairing mechanism in the cuprates. But as anybody who was around in 1987 knows, that superconductors are magic, and magic always comes with the expectation of applications. And one of the very fortunate features of my career is that I started out as a postdoc at the British High Energy Physics Lab, Rutherford Laboratory, in really at the time the world's best superconducting magnet manufacturing group. And it taught me that if you operate at this interface between the science and the technology, you are absolutely guaranteed to have a very large variety of interesting problems thrown at you. And that actually it's a very fertile way to work with agencies that are interested in applications, as well as those interested in the basic science. So my flavor today is, my goal today is really to give you a flavor of where the forefront technology in HTS, i.e. cuprate, high temperature superconductor cuprates, superconducting magnet technology is going. But recognizing that there's a broad variety of people here, I'm going to start maybe the first third of my talk will be some basic issues of superconductivity and where it exists. And, something about the key physics parameters that decide whether a given superconductor, and there are thousands of superconducting materials, but there's really only 5 or 6 which are useful. And I'm not going to deal here with anything, qubits and electronic uses. So there's really only 5 materials, and 2 of them are represented here: REBCO, rare earth barium copper oxide, of which the prototype is yttrium barium copper oxide, and bismuth 2212, i.e. bismuth 2, strontium 2, copper oxygen 10. So this is a hybrid talk, as I say, first some basics, and second, I'm going to go into a deep dive into the front line of trying to make ultra high field. And the danger of this, of course, is that I'm going to go into areas where, I just am not giving enough background to people. So I would encourage, if you want to, you could signal to the chair that, hey, I really didn't understand that slide, but I really would like to. And in this way, perhaps feel free to interrupt me so that the talk is more useful. So, I mean, here's the sort of very, very basic thing. Of course, I assume everybody knows this, but that may not be true, if you're a chemical engineer or something. So, non-superconductive metals, essentially the resistivity is determined by phonon scattering. And this is linear at high temperatures, but as you come down to absolute zero, you have essentially scattering determined by the 0 point energy. But a superconductor is just like that, except that at a critical temperature, suddenly the resistivity drops. And it really does go to 0. And for about 20 years after Kamalianis discovered this, that was the knowledge of superconductivity. But in the mid-1930s, Meissner and Oxenfeld started playing around placing superconductors in magnetic fields and realized that there was a second independent property, which was that whereas above the superconducting state in the normal state, magnetic flux just penetrates pretty uniformly, according to standard paramagnetic or diamagnetic behavior. But once you went into the superconducting state, you actually got a very strong distortion of the magnetic field around the superconductor due to the fact that the superconductor at that stage they were working with pure metals completely excluded the flux. And it was soon realized conceptually, and actually not for another 20 or 30 years, that this was because there was a supercurrent induced to flow in the surface of the superconductor, which was canceling the external field and generating this distortion of the V line. Now, is superconductivity exotic? Well, it's magic, it's exotic, but in the sense of, if you look at the superconducting elements, well, the black ones here represent elements which are superconducting at normal pressure, just as you buy them from Alpha Razar or whatever. And in particular, the early ones, mercury, lead, indium, tin, thallium, gallium, were widely studied. And then there are some more exotic ones here, the actinides. But there are a good number of other materials which become superconducting under pressure. And so I think one can say here really that the real issue is that most metallic elements are superconducting, except the very weak scattering elements like copper, silver, and gold, which implies that there is weak electron phonon coupling in these materials, and that's essential to the standard BCS theories of superconductor and metallic materials. And magnetic elements. And so for a long time, we thought, the anti-ferromagnetic elements, the ferromagnetic elements were never going to superconduct. So it was really extraordinary when that wonderful synthetic chemist, Hideo Hosono, 15 years ago now, created a huge excitement by making superconductors out of iron and arsenic. So even iron turns out not to be a forbidden element, but does have to be it does have to be alloyed. Now, there are two types of superconductors defined by two different kinds of magnetic behavior, and the elemental superconductors, so-called type 1 superconductors, have this kind of fairly standard second order phase transition curve where you have a superconducting state here and then a normal state out there. There's a critical field, which is temperature dependent, and then you get this transition. And neglecting situations where there's an inhomogeneous demagnetization factor, essentially the material is superconducting here and it excludes flux, as I showed, and up here then the flux enters. More interesting, and it took really an enormously long time to understand type 2 superconductors, because actually both experimentally this was discovered in a country, in a city, unfortunately being totally taken apart in this police action going on in the Ukraine, in Kharkov, in the Low Temperature Physics Institute. In the early 1930s, Lev Shubnikov, who had learned a lot of low temperature physics in Leiden, went back there. He was a very accomplished material scientist and crystal grower. And he started taking a type 1 superconductor, indium, and alloying it with lead and thallium and various other things. And he started to see evidence then of a different behavior at a much lower field, BC1. And then complete loss of superconductivity at a higher field, BC2, right here. BC here becomes now a thermodynamic parameter where the energy of the superconducting state is a half BC squared over 2 mu 0 per unit volume. But the physical changes occur at the upper critical field, BC2, and the lower critical field, BC1. The extraordinary thing was that Landau was in the institute at the time, and Shubnikov and his students were able to show experimentally this, but there was no theoretical way to understand all this. And unfortunately, not long after this, he was arrested, accused of being an enemy of the state, having been in Western Europe, actually was shot. And it became very, very difficult for anybody to admit what had gone on, including, most remarkably, and I never have had this explained to me, Landau, because Landau, of course, went to Moscow and in the 1950s developed the Ginzburg-Landau theory of superconductivity, and talked about the issue of type 1, type 2. In fact, I think I've got let me come here. He, coming out of the Ginzburg-Landau is this parameter kappa, which is the ratio of the field penetration depth to the coherence length. And he said, well, if kappa is less than 1 over root 2, it's a type 1 superconductor. If it's greater than 1 over root 2, it's a type 2 superconductor. But in the paper, he said, well, this is just a mathematical solution. It has no physical meaning. And it took his student, Abrikosov, to, in fact, explore this and understand that there were solutions to the Ginzburg-Landau equations when kappa was very, very large, which produced this quantized vortices within the material. And the important thing about this is that it enables the magnetic field, which is therefore, of course, raising the energy of the superconductor, to be lowered, because the magnetic field then enters as quantized vortices. So if you look here at the structure of these vortices are 2 coherence lengths in diameter, and the superconducting state then disappears in the normal core of all these vortices. And this enables superconductivity to exist to, in fact, now well over 100 Tesla, whereas in any pure metal, this is 300 or 400 millitesla, 500 millitesla, or something like that. So very, very weak. Now, from the point of view of using these things, basically the killer app for superconductors is the creation of very strong magnetic fields well beyond anything you could do with the saturation of iron, or in large volumes where you may require 1.5 Tesla in a very large volume, and the I squared R dissipation losses in the copper windings, which are saturating the iron, may be very expensive in energy. Of course, many electric motors now operate with strong permanent magnets, but nevertheless, I mean, you are limited there to rather low magnetic fields, down in this portion of the diagram. So, I mean, if you think of currents as creating magnetic fields, so H equals Mi in a long solenoid, then what you want, of course, is very, very high current densities. Typically cannot operate copper at more than about 10 amps per square millimeter before it starts to get very hot in dense windings. Whereas superconductors, and this is a plot that's kept by my colleague here in Tallahassee, Peter Lee, essentially these are whole wire critical current densities for the various materials that you could purchase and therefore use practically. Most is made of niobium titanium. It's the Large Hadron Collider at CERN. Most MRI magnets, well, essentially every MRI magnet is made of niobium ti. Gigahertz NMR magnets, which are a fairly large market, use niobium 310 inside niobium titanium magnets. But if we want to go higher than that from a superconducting point of view, we've got to use one of these cuprate superconductors. And so you see that critical current density characteristic extends, it's much flatter and extends out to much higher fields. And one of the tasks that we've been involved in here is to try and probe the upper limits of this. And so with a Rebco coil, 2 years ago, we published a new world record field of 45.5 Tesla with a Rebco coil, but we did a lot of damage to the conductor as we did it, because there are very, very large stresses associated with these windings. So this is the fun aspect of what we're doing. That's kind of those characteristics. So niobium titanium has been the workhorse low temperature superconductor since about 1970. But its upper critical field at 0 Kelvin is only about 15 Tesla. Now, to put that in perspective, the Large Hadron Collider at CERN uses niobium titanium magnets in superfluid helium at about 1.5 Kelvin. Dipole magnet is inherently inefficient magnetically as opposed to a solenoid, but it operates at about 8.8 Tesla. And so, maybe if you were truly heroic, you could get that up to about 10 Tesla. But in fact, niobium 310 is that next generation LTS. And the high luminosity upgrade of the Large Hadron Collider is using niobium 310 magnets in the intersection regions, quadrupole magnets, to squeeze the beam to get the intensity up much higher. And, so these are kind of dipoles. These are cross sections, starting with the Tevatron in the very early 1970s, Hera in Germany, Rick of Brookhaven, and the Large Hadron Collider. All of these used niobium titanium. And actually, they all use it in the key preferred form here is to have a round wire, and you cable this in a hollow flat cable, and you flatten the cable. This is a so-called Rutherford cable. Here, the copper, which is around each of these filaments, has been etched away, and so the black here are the niobium titanium filaments. And for a real accelerator, there are typically 1,000 to 2,000 filaments in each of these wires. And what that means is you have a very good superconductor, which is stabilized somewhat against slight electromagnetic instabilities by the copper. So if there's any sudden movement of flux in the filaments here, then there's eddy current damping, and essentially it becomes an individual local perturbation, not a collective perturbation. And so, you know, this is a technology that works very well. Now, the new driver in high energy physics is the Future Circular Collider. You know, this is there is a big European effort to do the background R&D for this. Here is the existing Large Hadron Collider on the CERN site. So we're looking south here towards the Mont Blanc. And this is an 80 or in other things, 100-kilometer tunnel. I think the rock gets a little bit dicey when you go out to 100 kilometers. So there's a desire, I think, to shrink this to 100 kilometers, to 80 kilometers. But you have to use now a different superconductor, and the idea is to go to 16 Tesla magnets. But this requires actually a much better niobium-310. And what I want to emphasize here is just that the high energy physics has been the single most important and sustained driver for superconducting conductor and magnet technology since the early 1970s. You have to bend the beam that you've generated, and so you need powerful dipole magnets to bend the beam. You need quadrupole magnets to focus it. And actually now you use superconducting radio frequency cavities to energize the beam with powerful gradients, which now exceed 20 megavolts per meter, and in prototype forms actually go over 40 megavolts per meter. So they're very, very, very compact acceleration. Now, I'm at the National High Magnetic Field Lab, where, and possibly some of you in the room come and use the magnet lab. Here, most of the magnets are brute force magnets. They are huge amounts of DC power, as high as 34 megawatts into a given magnet, 34 megawatts into a magnet that's got lots of holes. There's a huge amount of refrigerated, deionized water pumped through these holes to take the heat away. I think we have now 5 million gallons of deionized water, which is available for this. And these magnets go up to 41 Tesla now as purely resistive magnets. And with a hybrid magnet of 11 Tesla and niobium-310 and 34 Tesla of copper to 45.5 Tesla. So it's a great training ground. So NSF definitely would like us to be able to replace more and more of these with superconducting magnets, and that's perhaps where the rest of my talk is. So I don't know if that's a good place to stop and allow questions if anybody has anybody, but I'd be very happy to.
Yeah, absolutely. If there are questions in the audience, please speak up or post your question in the chat. I'll read it.
Okay, everybody's being very polite. All right, so one of the key things that happened when we got to the cuprates, and suddenly the highest temperature went from being 18 degrees Kelvin to 92 degrees Kelvin, of course, is that one could do experiments in liquid nitrogen. And possibly some of you were at this famous American Physical Society meeting, the Woodstock of Physics in New York City in March of 1987, when all sorts of wonderful things happened. And the meeting started, I think, at 7 o'clock the night before and finished, I don't know, about 6:30 a.m. So possibly a 12-hour session. But one thing that was not realized amongst all the hype was that these materials are bad metals. They are metallic. There are carriers in the material, but the carrier density is low. And you end up, therefore, in a situation where any sort of charge imbalances and atoms which are not on the right site can cause local perturbations to superconductivity. And above all, one of the most important perturbations, also sadly occurring in the iron-based superconductors, is what happens at grain boundaries. So there is always strain at grain boundaries, and this strain decreases the carrier density. It becomes more difficult to screen local charges and things like that. And so you end up with a situation where you have grains, crystals of very good superconductivity, but they are separated from each other by, of course, grain boundaries, which form a totally interconnected network where the coupling is either very bad if it's a very high angle grain boundary, or at a moderately misoriented grain boundary, there is a superconducting coupling, but it's weakened. And so actually what happens is that people said, you've got to go towards texture. And the first material which was generated this way was bismuth 2223, which looks really good because TC is 110 Kelvin. And there is a bismuth oxide double layer in these materials, which can be, it's micaceous. So in fact, if you put a powder of bismuth 2223, actually it's bismuth 2212 plus some stuff, into silver tube, you can mechanically fabricate that very well. But people found that the critical current density was much, much higher when they rolled it into tape, because the crystal structure is anisotropic, and this essentially gave a much better alignment of the crystals and therefore gave a higher critical current density. And it's interesting, this is the most mature of all HTS conductors, but frankly, its properties are just asymptotic. It's difficult to make this, or difficult to continue to improve it. But on the other hand, they have a very mature process. It's made by a company, Sumitomo Electric in Japan. And you can buy it. You can buy it in kilometer lengths. So I would say, however, for high field magnets, it's not plan A. And plan A is rare earth, barium copper oxide, where the rare earth may be yttrium. It may be yttrium mixed with gadolinium or something else. Everybody has. And what you do here, and I'll show you the architecture in a minute, but this is a real cross section. So you see, this is a tape. Previously, I was showing you round wires, and the tape aspect ratio is even greater here. So yeah, so this is something that you would tend to wind as pancakes and stack the pancakes one on top of one another, which is, well, okay, but it's not, in fact, the most desirable way of making a high field, high quality solenoid. But this is a very interesting material. It is the least anisotropic of the common cuprate superconductors because the charge reservoir layer has fairly good conductivity in it. It's much better, for example, than either bismuth 2223 or bismuth 2212. But we claim, and we about 10 years ago persuaded DOE High Energy Physics that for reasons that were not at all well understood at the time, you could make round wire forms of this bismuth 2212, and it had high critical current densities. So whatever was needed here to get a high critical current density was not needed here. And so we said this needs to be understood because of its properties. And in fact, what's happened by virtue of very nice support from high energy physics over more than a decade, This has now got the highest critical current density of any of the cuprate superconductors. And a big advantage of this is that although the material itself is anisotropic at the grain level, because we have all orientations here, it's macroscopically isotropic. And there are real problems in making magnets associated with dealing with the isotropy here, because this method of manufacture here is almost a single crystal by the mile. So it's an actual triumph of materials engineering, but it is, there are some nightmarish aspects of what happens when you have it. So the other issue is to say this, that superconducting magnets become attractive with conductors that can carry 500 amps per square millimeter or so. Copper is about 10 amps per square millimeter. And so you see, if we draw a line across here, bismuth 2212 definitely fulfills this. This I should change. Rebco is up here, especially parallel to the AB planes, which is where much of the magnet operates, but in fact, it is determined by the worst in the end. So the theme of my talk really is this, is Rebco is plan A, because you buy it, it's superconducting, all you have to do is respect the fact that if you wind it on too tight a bend radius, you'll crack it, and then you won't have superconducting continuity. And the other issue is classically magnets are back to being the principal driver for HTS applications. There was a period of 25 years where supposedly the whole electric utility infrastructure of the world was going to be transformed by, you know, all the transmission lines, the motors, the generators, transformers are going to be superconducting. And technically speaking, virtually all of this was shown to be true. But the problem is these conductors are extremely expensive, so there's no way you could afford it. And of course, you have to pay for the cooling technology. Very interesting, stay tuned, is really if compact fusion, which has had a tremendous amount of publicity real recently, and can escape any problem of a Theranos moment, they actually are demanding huge quantities of Rebco. So this may really drive down the cost. So some of this becomes possible. So stay tuned. 5 years out, that might be true. But another issue is this, HTS conductors will never be used where you can use niobium titanium or niobium 310, because these are essentially an order of magnitude cheaper under present circumstances. So at the present time, we've got many HTS magnet prototypes and one-off projects, e.g. the Magnet Lab 32 Tesla magnet, which took us about 7 years to build, cost about $15 million. There's a Tohoku University in Japan, 25 Tesla user magnet. There's some magnets in Korea. But there's only one serially produced magnet, which is a 1.2 gigahertz NMR magnet made by Bruker Biospin. They've now delivered 3 of these. And I think they have orders for about a dozen. They're about $15 to $20 million pop. Part of the problem here is that there are many ways these magnets can fail. And one of the arguments I've been making is that if we want these magnets to be ubiquitous, we've got to be much more sharing about the way our magnets failed, so that one doesn't have to keep learning all these things. Now, this has taken a huge effort. Probably collectively, national governments invested a few $1 billion in trying to drive HTS materials into the electric utility industry. And in particular, there's a really very clever scientist, Ijima-san, who still works for a Japanese cable manufacturer, Fujikura Limited. And he talked about biaxial alignment. So the idea here is to avoid this grain boundary problem by getting all the grains to line up so that the excellent current density in one crystal can connect with the excellent in another. Now, the point of bringing this is just to say that sometimes things take a very, very long time. So, you know, this is now 30 years. And the nice thing is that I think Fujiko will supply the conductor for Brooker Biospin. So you can go buy this material now from multiple sources worldwide, in the United States, in China, in Japan, in Russia, and other places. What I want to say is that the price of these tapes, typically 4 millimeters wide, are about $40 to $50 a meter. So what we're looking at here is about 120 meters, I think, on these spools. So you're looking here at 120 times that. So getting on for, what's that, for $5,000. $5,000 worth. Well, on one side, it looks great, right? I mean, it's all coiled up beautifully. On the other side, what on earth is this rippling here that we're looking at? This, by the way, is not so uncommon. So this is the American manufacturer, Superpower, the cartoon of what we have. And so what you have is a very strong cold worked superalloy substrate, a nickel base alloy Hastelloy. And this has to be rolled to very, very, you know, smooth thing. It's then electropolished. You then put a solution of oxide onto the surface to utterly smooth it. You then come along and you deposit magnesium reactively in an oxygen environment, so it produces magnesium oxide as it goes down. And at the same time, you hit it with an ion beam. And the ion beam, it's a very well-defined angle, produces the almost instantaneous texture in the MgO that is manufactured. So with less than 50 nanometers of MgO here, you have a perfect 100 texture. But it's very, very thin, so you grow it homoepitaxially, perhaps to double that thickness. It's, however, not protective of nickel diffusing out, and so you put down here lanthanum manganate. And then finally, you have a substrate. All of this is done at room temperature, where you can now grow yttrium, barium, copper oxide in situ in various ways: pulse laser deposition, magnetron sputtering, MOCVD. And then you grow that layer on the top. You have to protect it because the YBCO is sensitive to the atmosphere with sputtered silver. And then you protect it even further, or you protect the conductor with quite thick copper stabilizer. So this is the cartoon, this is the reality, and a couple of young guys, Korean postdoc now on the staff, and a young recent MS graduate, Michael Small, who've been working on this. So what does it look like? Well, of course, it isn't like the cartoon. So these are the edges of 4 pieces taken from this. So here is the Hastelloy. The black layer here is the kind of 1.5 micron thick Rebco and base oxide layer, which is doing the work. And then you can see, I think, a little white silver, and then there's copper, which is electroplated. The thing is that this is made wide, typically 12 millimeters wide, and then you have to slit it, because the the current that it can carry is too high, and actually it becomes unwieldy to wind things which are too wide. And so the standard method of cutting is kind of a high-tech pizza cutter. But in this particular case, this high-tech pizza cutter is kind of shearing as well as cutting. But it seems to be, you know, these are centimeters apart. So here it's not bad, here it's terrible, here it's terrible, here it's not too bad. But, you know, this these are topographic height scans. So here is the Here is the edge of the conductor, and you can see that there are all these red hot spots which correspond to this thing. Well, now imagine you're winding a pancake out of these, and so these are all tight up against one another. There are very high stresses anyway in this situation. So you get very highly localized stresses as well under these circumstances. So you have to worry about things like this. And so, the other issue is that the internal chemistry of these conductors has been a wonderful playground where you put nanoscale precipitates into the material and things like that. But difficulty about this is that when you're growing such a film at 750 centigrade or thereabouts, you have to utterly control the nucleation of what's growing. Otherwise, you don't get something consistent. And I could just say, maybe make this point, that this is what happened. We got about 10 kilometers of tape for our 32 Tesla magnet. And this represents the timeline going from left to right. And they specify their tape based on a 77 Kelvin liquid nitrogen cell field. And actually, they did a very good job there. You see they're around between 125 and maybe 150 amps. But here at low temperatures where we were making our magnet, God, look at all these incredible fluctuation of properties. And this is because of the very complex interactions that occur between the quantized vortices and these insulating defects in the material which enable the establishment of flux density gradients. So here are some pictures. I won't go into the details of this, but these are all made to the same specification. What we're looking at here are columns, nano barium zirconate, and they're all to the same magnification. So you can see here the density is lower, the size is bigger, here the density is lower, so here the density is highest, here it's even lower. And so this is at low temperatures 6 megaamps per square centimeter. This is 3.7 megaamps per square centimeter. So we have something which is not reproducible. And the other issue is that because of the anisotropy of the material, and because of the fact that the manufacturer has really made this kind of single crystal by the mile, the critical current density is a strong function of angle. So for example, these are torque magnetometer measurements. You can see, so it goes 30 degrees away from the AB planes, 6 megamps per square centimeter, but along the AB plane, right, 30 megamps per square centimeter. So this is very important because in the solenoid magnet, most of the material is operating actually close where the magnetic field is close to this direction. But in the end windings where there's a significant radial field, the critical current drops. So the classic point is typically here. But the other difficulty is you get very large torques that develop when the conductor tape axis is not parallel to the magnetic field axis, and very often that generates damage. So this is one of the issues that we're sort of trying to understand. So part of the problem is that with this very complex and in principle highly optimized nanostructure development, everything is beautiful except when it isn't. And so you need some kind of tool that can tell you. And the manufacturers use basically an induced magnetization. They have a whole probe array and they run everything through the whole probe array, but there's no magnetic field present. And so if you want to understand the role of the defects, you have to have some device. And so we have a device where H can be parallel to the C axis or parallel typically anyway to the AB plane, but we actually use a rotating permanent magnet. So it's quite versatile. And when you do things like this, you see that the critical current density can be pretty good, but it's not perfect. But this is definitely pretty good, and I think would be quite acceptable. But here's stuff that we got from another vendor, quite reputable vendor, and this was so awful, we thought, oh golly, our apparatus is bad. This is essentially a reconstruction of the magnetic field generated by induced screening currents as measured by an array of 7 hole probes. But here's it going in one direction, here it's going in the opposite direction. So this variability is just there. And sometimes, in fact, you see as they lose control, maybe in this case it's a conductor made by MOCVD, there's an MOCVD burp in the shower head, and that burp in the shower head actually locally inverts the critical current density due to the fact that here we lost those C-axis nanorods, and we got some jumbled array of mass. So the mini summary is we can buy conductors from 5 to 7 major suppliers, which is good, but do we really know what we're getting? Not yet. But nevertheless, this is the plan for most UHF magnets, because you just buy it and you wind it. Okay, so if you can afford to pay these prices, then you do. And we believe in it too. But there's an alternate, and this is perhaps the last, I'll just stop this not to be too long, but here I think is something where we determined that we wanted a round multi-filament conductor, wanted to go back to bismuth 2212. But the grand challenge is it's not superconducting as delivered. And so we must take responsibility for making it superconducting by heat treatment. We have to do that in 1 bar of oxygen. We actually have to melt the bismuth 2212 inside a silver tube. And so we actually go up to about 890 degrees centigrade, typically 889. And so we have this kind of complex heat treatment. When it melts, it ejects oxygen from the structure. We then go through a very carefully controlled solidification process by which we get very sparse nucleation of the 2212 plates from the melt. And we allow this sparse nucleation to gobble up misoriented grains. And so the reason that this works as a round wire conductor is that we're capable of generating a biaxial texture. It's not as good as the biaxial texture in Rebco, but it is pretty good, purely by thermal methods. And so this is how we get the very high current density. And then we've lost oxygen up here, so we've got to let the oxygen keep going all the way down here. But the other issue is that because powder and tube has kind of 30% of void space, typically air, i.e. nitrogen and oxygen, oxygen can freely escape through silver, but nitrogen can't. So unless you provide an overpressure of, in this case, argon, so we have 49 bars of argon, 1 bar of oxygen, then actually it just bubbles and blows out and blows up the conductor. So this 50 bar is necessary. So we had to develop all. The other issue is the conductor is weak. Silver is not a strong material. Its elastic modulus is not strong, and so we have to reinforce it, and then we have to apply the insulation before winding, before reaction. So there were a lot of things, and it's taken us about a decade. But here are the conductors. These are what the conductors look like. So it looks actually like an niobium titanium or niobium tin conductor. And then after reaction, after having gone through the liquid state, there is some growth together of these filaments, and that has an effect. But the great advantages of all of this is that we have a round, we can use Rutherford cables, it's macroscopically isotropic, it's multi-filament with a low hysteretic loss, small screening currents, and it's easy to fabricate. So all of these are good things. So what can one say? I could certainly go into detail on this, but I don't. Perhaps is just to say that we had to make sure that in coils in particular, that this was a robust. So this is a coil after reaction. It's very clean. What you see here is an aluminosilicate insulation over the wire. Here is the Rutherford cable. Yeah, and we're making we're making magnets at the moment with Oxford Instrument Company and Cryomagnetics. We're aiming initially for 25 Tesla magnets, and we're happy. But we have to do a great deal of modeling here, because in a solenoid, the dominant stress is a hoop tension on the windings, which is just the product of the critical current density of the conductor times the B field times the radius of the winding. And you very, very quickly get to situations where the hoop stresses are 3 times the breaking stress of the wire. So that's not going to work. Here are the elastic strains. So what you have to do is put reinforcement into the windings. So this is, somebody commented on patents. This is one of the things that we did. We developed this quite slowly with many prototypes and developed a strong patent portfolio, which is the basis of being able to license the technology. Now, one of my colleagues does very detailed strain critical current measurements. And so what you can see here, the strain critical current, is that you start to damage at a strain, actually, if you look really very closely, at about 0.4% strain. But you can see that this is very progressive, so 0.6%. So these are not materials that fracture catastrophically. And so this is what has enabled us to design some interesting magnets. And in fact, we're going now to build a 28 Tesla at least solid state NMR quality magnet that we hope to finish in the next couple of years as we get NIH funding to enable us to buy the conductor. We do a lot of prototypes, for example, so we'll make a magnet, cut it apart, measure the critical current of all of these things. And so in this particular case, we noticed that one magnet we had made, we were able to localize damage to one set of voltage taps. And what happened here is that this was a reinforcement layer. So these inner turns here were reinforced with a strong ceramic fiber in the winding, but we got a delamination between that ceramic fiber. So everything is filled with epoxy resin, and so vacuum impregnation after winding. And you can see this kind of damage zone here. So these sorts of things are very useful to us as we develop the technology. And the other issue is just to say that lots of people are frightened by the idea of 50 bar furnaces and things like that. And it took us, we initially bought a commercial furnace from the company Deltec, and we found that as delivered to us, it had all sorts of leaks and thermocouples and control. So, but having rebuilt it ourselves, we've been under very, very good control. And I'm very pleased to say that our furnace tech, Lamar English, is an Alabama boy. He's a cave diver, so he knows all about high pressure oxygen tanks. And so this is our big Deltec furnace, which has a hot zone, which is about 14 centimeters in diameter and 45 centimeters long. And on the basis of this, he designed and built, well, the pressure vessel was built by a commercial fabricator, but essentially the whole system has been put together. And this is now 1 meter long and 25 centimeters in diameter. And this will lead to prototype dipole magnets for the future circular collider. So in summary, I would say there are undoubtedly complications to making magnets from bismuth 2212. But the great thing is that all issues have been solved individually, and now we're at the stage of solving all issues simultaneously. we think this technology is going to go commercial. Great thing. So I would just say that although I'm the one giving the talk here, I benefit from a huge variety of wonderful colleagues, scientists, as well as graduate students. So particularly PhD students, Griffin, Bradford, Ashley, Francis, Paul Hu, now back in China at Plasma Fusion Institute, Yavu Zha's recent PhD, Michael Small, I mentioned, as well as we have great collaborations in Korea and Japan. So thank you very much. Happy to answer any questions if you have any.
Thank you very much for your very informative talk, David.